in 60 minutes or less. This is a humbling topic, not only because of its scope, but also because so many of you in the audience have made profound contributions to this field, and so it feels a little bit like a doctoral exam or something here. So thank you for the opportunity. I'll try to give a high-level overview of this field for those maybe who are a little less acquainted with it. So for context, I'm speaking to you as a numerical analyst, thinking of working in double precision arithmetic and actually doing computations ideally. And every norm that you'll see will generally be the Euclidean norm or the operator norm it induces. And so just kind of keep that in mind as context. And so I'm interested in solving AX equal B through a variety of algorithms. And Olga told us a little bit at the end of the lecture last night that we could maybe just solve this using fast matrix multiplication and a block rendering of A. And so that's one approach one might take algorithmically to find minimum complexity. We're not taking that approach. We're looking at more conventional algorithms. Now, to the pure mathematicians in the audience, this is a very simple problem. We just write x equals A inverse B and declare victory. And we need to go a little bit farther than this, although in theory we're quite happy to do this for analysis. But we want to compute, and in particular, we're not going to compute A inverse itself. That turns out to be something like 3 times more expensive. Just as an analogy, you might imagine in your linear algebra class, Gaussian elimination versus Gauss-Jordan elimination to construct the inverse, right? That was more of a pain of a problem. You had to solve more systems, right? And so we want to solve AX equal B, maybe without getting our hands on A inverse explicitly. And so all of these algorithms will have some flavor of solving the system without inverting a matrix. I will also limit myself to this square invertible case. If you have an underdetermined system of equations, then you have the freedom to choose many solutions. You might choose the one with greatest sparsity or least norm, something like that. That's a different business. If you have an overdetermined system, there's no solution, but perhaps you might solve that in the least squares sense, perhaps with some regularization or lasso kind of penalty. Chris might talk a little bit about that in the next lecture in terms of least squares problems. I'm focusing in this hour on the narrow problem of just AX equal B for invertible square A. And first, just to set our objectives a little bit, what is realistic to ask? So it's not realistic to solve this system exactly in floating point arithmetic. And so I want to follow up a little bit on Olga's discussion of forward and backward error from yesterday.
Very naive.
Yeah, absolutely.
What does realistic mean in this?
Well, I'm about to, let me describe what goal we might have. So we want to solve AX equal B, but perhaps we also might think of a nearby problem, A plus E x hat equals B plus E. So before we do anything, maybe we'll just think in a very pure non-computational way about how much the solution to AX equals B can change if we make small changes to the data. And that should then set our expectations, because we will indeed be making small changes to the data when we store it, when we compute with it, and so forth. And in that case, one can derive a variety of bounds, and they all have this kind of flavor. I like this one because it's not asymptotic. It's a concrete bound. So if I need to pose a condition here. If I presume that the norm of E is less than epsilon times the norm of A, and the norm of E, little e, is less than or equal to the epsilon times the norm of B. So in other words, I'm making small changes to the system. Then the solution can change as much as 2 times epsilon divided by 1 minus epsilon times the norm of A times the norm of A inverse times this crucial factor, the norm of A times the norm of A inverse, which we call the condition number.
So can I try asking a question again?
Please.
So I know how to do this with n-cubed arithmetic operations.
Yes.
So to you that's unacceptable. So
No, that's acceptable. N cubed is great.
So now I'm really confused.
Okay.
So, I mean, Gaussian elimination.
We're talking about Gaussian elimination.
This is roughly n-cubed arithmetic operation.
Absolutely. We're talking
But
about
you
flavors.
told me that's not acceptable.
No, I said inverting the matrix A is not acceptable. So to us, there's a difference between solve. So think of a basic linear algebra class. If you're solving with Gaussian elimination, you set up an augmented matrix, you put the vector b on the side, you solve that system, you get an x at the end. And just as an analogy, compare that to Gauss-Jordan elimination.
So
where,
I forget what Gauss-Jordan is.
you build A, and then you put an identity matrix next to it, and you then turn that identity matrix into the inverse. That's more work, right? But then you have an A inverse you can apply repeatedly, if you like it that way. We will do Gaussian elimination in 2/3 n cubed operations, and then have a factorization of a matrix we can reuse. Jim might illuminate.
And also, computing A inverse is not backward stable.
Okay, yeah, another right. Okay, another good reason. Yes. Okay.
So you're like very happy if you go from n cubed to 2/3 n cubed. That's the kind of question I'm.
Sure. So inverting. So building A inverse might cost 2 n cubed operations. Solving what I'll call the LU factorization will be 2/3 n cubed. And that's the way we will go about doing business. But I want to kind of survey the landscape. And so maybe when I get there, your question will either be resolved or sharpened.
Okay.
Yeah. Yes?
So yesterday, I think it was Olga who made the statement that the condition number tells us the distance to the nearest unstable problem.
Exactly. That's the point Jim made to me, to emphasize here, is that the distance of A to singularity is 1 over the norm of A inverse. That is to say, 1 over the norm of A inverse tells me how close I am to making a perturbation that gives A a 0 eigenvalue.
Okay.
And so this condition number can be seen as a normalized version of the reciprocal of the distance to singularity. The farther you are from singularity, the better the conditioning.
This is L2
Many of these things can be generalized to other norms. This is all a two-norm statement. You prove this with the singular value decomposition. And you can build that perturbation that turns A to singular explicitly with the singular value decomposition. Okay. But the key point here is this epsilon describes the size of your backward error, the error you're making changes to A into B. The condition number gives you a magnification factor that describes what kind of forward error one might expect given a certain amount of backward error that we would incur.
Is this, should it be the relative error is bounded by the right-hand side? And what if there's no norm of x on the right-hand side?
I think we control that here, yeah. You could scale everything, but you'd scale, yeah, A and B.
I guess the question should be x minus x hat divided by the norm of x.
Yeah, I'm not sure. I'd have to look that up. I may have made a mistake there. Yeah. Yes.
Bit inequality. Whenever you write the A inverse, is the condition number, is that multiplied to the symbol on the left, or is it only in the denominator?
Right here.
Yes. Sorry. Is there also? Yes. So this
this
here
is-
is actually part of the equation.
What's that? The norm of A inverse is part of the equation. It multiplies this factor. Yeah. There's a little dot. Good. I love the questions. We're talking across communities, so.
It has to be normalized on the left-hand side because the right-hand side is scaling variant.
Yes, that's right. Yeah, good point. Yeah, thanks.
Norm, you have to tell us which norm. You take the.
I said two
greater
norm. Everything I say will work for the two norm, just for simplicity and the confines of this lecture.
By two norm, you mean operator norm?
I mean the Euclidean vector norm and the operator norm it induces.
Wait a minute. Euclidean norm,
Yes? What's that?
not operator norm.
The Euclidean vector norm and the operator norm it induces. So-
Matrix, you mean
Normal
the operator.
matrices.
So when I'm a matrix
Vector
operator norm.
Euclidean
So
norm.
the norm of x is the square root of x transpose x, and the norm of ax is the max.
Only the vector star.
Okay, where this is Euclidean norm, just to show you right.
Unfortunate notation.
In the sense that I'm overloading, I'm overloading the norm.
I'll ask you later why you think it's helpful.
That's a critique of the field, not just the presentation. Okay, shall we solve some systems? Okay, all right, thanks. And we'll get as far as we can get given good discussion. Okay, so the method of choice for, first of all, we're going to talk about direct methods versus iterative methods. And I'll try to give you a flavor for both of those, and we'll see how far we get on the iterative methods. I don't want to dwell on the direct methods. But there's a great picture in Trefethen and Bao. It's a book on numerical linear algebra that's time versus, say, residual norm or error. Let's just be vague about that. Direct methods do a bunch of work and then give you, in principle, an exact answer, but a suitable answer at some fixed time. Whereas iterative methods chip away at the answer and give you a partial solution, where if you only care about a few digits of accuracy because your method is a discretization of a partial differential equation that's only accurate to some threshold, then you might be very happy with an iterative method that converges like that. But Hen is not happy with methods that converge like that. He wants methods that converge like this. And occasionally, when you run some of these methods, you get methods that converge like this. And so iterative methods are living dangerously, and, but have the potential to give incredibly quick convergence if you set the problem up correctly. And so I want to try to give you a flavor for this distinction. Often direct corresponds to dense matrices, although there are sparse direct methods I'll hint about. And iterative corresponds to what we call sparse matrices, where the convention, I guess going back to Wilkinson, is to define sparsity as a matrix that has enough zeros that it pays to exploit that zero non-zero structure.
Roughly speaking, what's the threshold for that?
Usually order n non-zeros in an n by n matrix. But again, that's just a rough rule of thumb. Okay, so some words about direct methods. So I'm talking about Gaussian elimination.
Just a comment, companies are building accelerators when it's 50% sparse, but they still move faster.
Wow, okay, that's so here the idea will be that we're going to take a matrix A and we'll factor it into the product of L and U, where L is unit, lower triangular, where unit means one's on the main diagonal and then the upper diagonal is otherwise empty, and U is just upper triangular. And we like this factorization because then if we have AX equals B, then we can solve, of course we have LUX equals B, so we solve LY equals B with forward substitution. And then we solve UX equals Y. Solve the first system for Y, the second system for X, using backward substitution. And both of these are exactly n squared floating point operations. Okay, so if we have such a factorization, we can do these steps to solve a system, and then we can reuse the LU factors for as many systems as we like. Of course, A inverse is U inverse L inverse if we really wanted to think of it that way. Danny Sorensen likes to, and maybe many others, like this kind of bird's eye view of what's going on. If we partition our A into this form where we have a 1 by 1 block and an n minus 1 by n minus 1 block, then we can imagine this as one step of this Gaussian elimination process will result in a part of a unit lower triangular matrix, an active matrix that's a rank 1 update of the old 2 by 2 block, and then a portion of the upper triangular matrix that we're trying to compute. So you can see the L and the U emerging here as we're still working on this middle section. But maybe looking at this formula, you can see something that will go wrong potentially, right? What's the issue? Oh, you weren't so shy before. We could, yeah, what if alpha is 0, right? Then we divide by 0. What if it's close to 0? Then suddenly L has factors in it that are much larger than the factors in A. And so if you were doing this by hand in an elementary linear algebra class, you would just say, well, I'll eliminate using a different equation. And so that's essentially what we do in practice. So we have Gaussian elimination, which we abbreviate GE. And it gives you A equals LU, and that happens in about 2/3 n cubed flops. Yeah, I better not call that 2. Okay. The alternative that we can implement to add stability is partial pivoting, which is row swapping. This is what we would do if we're doing it by hand and we would run into one of those alpha equals 0 problems. There's a way to permute the rows of A to give you an LU factorization, and that row ordering takes order n squared comparisons. At each step, you're going to search down this column and find the largest entry in the column, and you're going to swap to put that in the 1-1 position or the 1-1 position of your active submatrix, and you'll update that way. So Gaussian elimination is unstable. As you can see, it doesn't even exist for some A that are very nice, like 0, 1, 1, 0. Partial pivoting is almost always stable. And I don't say that in a kind of measure theoretic sense, but just in the sense that there are examples where basically no pivoting occurs and you still end up with L and U that have enormous entries, exponential in the dimension. And those examples sort of break Gaussian elimination with partial pivoting, but they're thought to be incredibly rare in practice, to the extent of having never, if hardly ever, arisen in applications.
Geometric description of those bad matrices that we tested? Like
I don't know, Jim, do you have a good geometric description of those?
So there have been a bunch of papers on the probability of large pivot growth. So I can't remember exactly who wrote them, but yes, they exist.
I think Leslie Foster's done some work on that.
Yeah, it's been a while.
Yeah.
But they're not tight conditions. You can give sufficient conditions for there to be bounded pivoting, and then you can probabilistically those conditions are unlikely to occur.
I'm
But
actually
we
more
still lack
interested
it.
in the bad ones.
So, yeah,
There's a test to tell you it's going to be bad.
not going to.
I think you do it and then
Running
you
it.
see that L and U have large entries in them.
Yeah.
But a priori, it'd be nice to predict. Yeah. Okay, so the solution, if you're uncomfortable with that, is to do complete pivoting. Which also swaps the columns, but that adds order n cubed comparisons. And for that reason, that's usually unappealing. And if you really care about stability to that extent, maybe you want to solve a system with QR with a singular value decomposition or something that gives you even more, perhaps even more information. Okay, so living dangerously, perhaps, numerical analysts typically, when you want to do backslash in MATLAB, you're going to end up doing some flavor of Gaussian elimination with partial pivoting. Okay, yeah?
And people have also done randomized. So they
Yes.
pre-multiply A by half random NMR and then value with no pivoting.
Joel and I were talking about this last night. Random pivoting, ideas too. Random row ordering.
No, this is different. This is
Random row ordering.
This is putting the matrix in general position so that you don't have to think about pivoting it.
Yeah, that would be a nice thing. Yeah. Okay, so moving on.
A question, because you said the Gaussian elimination is unstable,
Mhm.
without people
Yeah.
Is that this? I remember there was a paper by Richardson, I think, that uses Gaussian model and then condition number goes up. Related to that, it's different.
There's a paper by Trefethen and Viswanathan and Trefethen on triangular matrices, condition number of triangular,
Yes, that was-
random
this is the
triangular.
paper.
That's where you get exponential growth in the
This is
condition number.
related to that, or not?
Not so much in the sense that you don't end up with those systems so much. But
So who-
Nick's also been interested in conditioning of Gaussian matrices.
Okay, what
Yeah.
is the statement that Gaussianization without pivoting is unstable? Is there a theorem behind, or is it an empirical observation?
Certainly there are empirical observations. They could be easy to write a
Question is
theorem.
whether is there
Yeah.
something,
There are examples.
Yeah, I mean,
I
yes.
mean, like you could write down a matrix where things,
just the growing, numbers growing like crazy?
Something like, I mean, variants of this problem, right?
Okay.
Okay, so maybe just mentioning one other very special important case is if we have a symmetric positive definite A, then we do something called the Cholesky factorization, which is to say A equals L, LT, where L is lower triangular, and we do this in 1/3 n cubed time. And there's no need to pivot typically, and there's nice stability results for Cholesky. And Joel's also looked at some interesting random things with Cholesky as well. Okay, there are other structures you might take advantage of. Here is just a flavor, but if you have a Toeplitz matrix, or if you have a Hankel matrix, or structures of this form can potentially be exploited, and the question then always is the fast algorithm stable, and you might want to investigate that. The other class of structure I'd like to talk about is sparsity. And we mentioned a little bit of what a sparse system was. I'll come over here. I'll just say many non-zeros, keep it simple.
Many zeros, right?
What's that? Oh, many zeros. Yeah, sorry, thank you. Yeah, many non-zeros too, as Jim was saying. Okay. All right. Yeah, exactly. That's a lot. N's big, right? Come on. You're being picky here, Dan. Okay. So the idea here is that we have a graph representation of A. And I just mentioned, because some of you may, from the TCS world, may find this interesting, is annotation. So the adjacency matrix showing how the entries in A, you have a connection in your graph between nodes J and K if A, J, K is non-zero. And you can do Gaussian elimination on the graph to get kind of an elimination tree. And you can potentially relabel your nodes to minimize, we call fill-in. And John can tell you all about some of these clever graph ordering algorithm, graph labeling algorithms to try to basically minimize the bandwidth often of the system. But I thought maybe I would show you an example to kind of break up the lecture. So if we could go to the slides. You basically go through the steps of Gaussian elimination to see when you would need to introduce a new node that was basically previously zero, or a new edge. And so if we go to the slides here, a little story to break up the talk. So in the late 17th century, Oxford had a problem. The undergraduates were too rowdy at their graduation ceremonies that were held in the University Church of St. Mary the Virgin, and that was indecorous to the faculty. And Christopher Wren designed a new building that was modeled after the Colosseum, except in England it rains too much to have an open-air amphitheater. So a roof was needed, but there were insufficient timbers to span the entire roof. And so John Wallace, a faculty member, a professor at Oxford, designed a potential roof structure that was built of interlocking beams, nicely dovetailed together here. And when my students complain about 4x4 linear systems, or when I complain about 4x4 linear systems, I show the system that Wallace came up with. So he wrote some kind of, I guess, force balance, I presume, equations, and various letters that correspond to spots in the graph. And there's an ampersand because he ran out of letters. And it's all in terms of a common parameter, scaling factor. And so this is a system of 25 equations. And he shows his work. This is just a small snippet of him doing his elimination. And of course, he's going to be very worried about, I'm sure, about this phenomenon called fill-in the sense that he doesn't want these equations to grow in length involving more variables. Here's his solution as rational numbers. And he nailed it. It's perfect. I put it in MATLAB and said, surely he made mistakes. He nailed it. So if we look at this structure, often what we see in problems and coming from engineering, for example, is that the structure of the physics gives us some information about the connectivity of the matrix. And so if we draw the graph for Wallace's matrix, we get something that looks like this. It's just one rendering, maybe not the best, showing the connectivity. And that looks maybe a little bit like a mess. But the thing to notice is that you don't have like n edges coming out of each of these nodes. You have maybe 4 edges or so. This is the graph of A plus A transpose. So I drew it as an undirected graph, even though Wallace set this up as a non-symmetric matrix. If we do Gaussian elimination on A, we see here's the sparsity pattern of the original A with 69 non-zeros. And when we do Gaussian elimination and we look at the magnitude of absolute value of L plus the absolute value of U, we get this structure. And so we can see the amount of fill-in. I learned from Chris Beatty what he called the flashlight trick. Imagine you stand over here and shine a flashlight from this side of the matrix and a flashlight from above the matrix. Anything cast in a shadow is a potential fill-in. And so we see not all of those entries fill in, but many of them do. And so I thought, well, this would be a really neat example for this talk to do a graph reordering and to find an example with less fill-in. And using the standard algorithms, I couldn't. And so that occurred to me, yeah, Wallace had a real reason to try to find a good labeling of these nodes. Maybe it was accidental, but surely he wouldn't have wanted something with a lot of fill-in. That would have created much more work. Okay, so.
When you relabel the graph, are you trying to minimize this predicted fill-in by the flashlight?
Exactly. Like you might say, this is kind of problematic to be way out here, right? There's a potential for lots of fill-in there. And so we'd really like to be able to maybe pull these in closer to the main diagonal, have something with some tight bandwidth, for example. So those are heuristics that are used to try to develop graph relabeling algorithms. Yeah.
What is the absolute value of L as?
Oh, that's just, I'm just being very careful that none of the diagonals in the, just the entry-wise absolute value. I just want to make sure there's no cancellation on the main diagonal. It's being pedantic. It's basically how many non-zeros are there in L, the lower triangular part, how many non-zeros are there in U, the upper triangular part.
So when the fill-in could occur by the flashlight prediction, but it does not, does that mean that there's like some fortuitous cancellation?
Yeah, some other zeros in other parts of the matrix, yeah.
Okay.
So in this case, the idea of relabeling is to bring things closer to the diagonal because there happens to be diagonal entries, right?
Right.
Is that like a sort of high-level intuition used for relabeling in general to push towards the diagonal regardless?
Right, so the most famous example is maybe the arrowhead matrix, where if you had a matrix that had non-zeros here and non-zeros here, you would fill in the entire matrix. Whereas if you swapped rows and columns so that you had diagonal plus bottom row and rightmost column, you would have no fill-in. So, yeah, that's an extreme example of what can happen.
Okay, and so so this is going to very much depend on like what the non-zero pattern of A happens to be.
Absolutely.
Okay.
Yeah. And then questions about whether you pivot or not and so forth.
Right,
Yeah.
and it's not always just about bandwidth. Al and George showed
Yeah.
that a two-dimensional checkerboard graph is asymptotically better if you do something else besides minimize its bandwidth.
By bandwidth, you mean getting closer to the diagonal.
Yeah.
Right.
Yeah.
So it's not just about bringing things to the diagonal.
It's hard to find the best.
Yeah.
So
Yeah.
have to approximate.
Yes.
Is there some kind of complexity on searching through the possible sparsity patterns, like going through the n-squared entries and figuring out what the sparsity is?
Yeah, I think that's what Jim was just referring to, is basically NP hard to find the best one of those. So we have heuristics that do a good job. Okay.
Is there any provable, like you can get, twice as close or like within a factor
Yeah,
of 2?
I'm looking at John because he's the expert
You
in
can
this.
get
yeah.
within polylog by finding separators in the graph, at least in the symmetric
Of the minimum,
case.
I think of the minimum bandwidth.
So if it's like an expander graph, there's no good way
That's right.
to solve it.
That's right.
Okay.
Hardness of approximation. So
Pardon?
NP hard, how hard is to approximate? So is this tight?
I don't know.
I think there's a line.
The one structure I didn't mention that I probably should have is banded structure, where we can do Gaussian elimination and n times the bandwidth squared. So we have many non-zero, we have all of our non-zeros focused within some bandwidth b of the main diagonal. That turns out to be another very nice case. Okay. Do we have time for some iterative methods? Good. Okay. That's
I want to hear about iterative.
good. Okay. All right, we're talking about iterative methods. Okay. We have at least 25 minutes for iterative methods here. Okay. If we could go back to the boards here. I'd like to talk briefly about a few kind of classical iterative methods and then explain some of the more modern methods, the so-called Krylov subspace methods. So the first class I'd like to talk about are stationary iterative methods. Jacobi, Gauss-Seidel, etc. That, or maybe a better term is splitting methods. The idea is we take a matrix A equals m minus n. We're interested in solving ax equals b. So this means m minus n times x equals b, or of course mx equals nx plus b.
So, is there any
M invertible. Ideally, easily.
So the situation is someone hands you M and N, or you are handed A?
You're handed A, and you're going to solve it some way, and you have some ideas about.
In some clever way.
So, for example, M might be the diagonal part of A. That would be a particularly nice matrix to invert. I sketched this out this way to give you some idea of like how you might encounter this method or invent this method. So, with this splitting, we get this tautology. To get an iterative method, we assume that we know some guess xk, and we'll use this to give us a solution at the next step. And that solution at the next step will involve solving a linear system involving m. So m better be easy enough that to solve one linear system, we can solve another linear system a lot. And then the question is, well, how does this converge? And one of the reasons to talk about these methods is that I think that the convergence theory is quite straightforward to work out, and I can give you a flavor for how that looks and actually prove something here. Okay, so we're interested in measuring the convergence of an iterative method through the norm of its residual vector, which in this case would be b minus a xk plus 1. And the exercise is to find an expression for the residual in terms of the previous residual. And so if we substitute in m minus n for a, that would give us m xk plus 1 minus n plus n xk plus 1. We substitute in the iterative method for m equals xk, for m xk plus 1. So that would be n xk plus b plus n, and we could substitute in the iterative method for xk plus 1 as m inverse mxk plus 1. And then we have another expression there. Cancel the b's. And put in the identity. And then we'll have n m inverse mxk plus 1, which would be n xk plus b. So there's some simple substitutions there. And I think then I can factor out, if I haven't made a sign error, which I fear that I have. That's right. That's right. Let's just see where. Oh, I have a minus here. That's what I was overlooking here. Okay, so what this is then is n m inverse times b minus m minus n xk, which is to say n m inverse rk. Wow, okay, it should be a delight from the audience. Okay, because what that tells us is that rk equals n m inverse to the kth power times r0. Ooh and ah, okay. Because this gives us a really easy condition now for categorizing whether we'll converge or not. It depends on whether we have matrix M times n inverse. What would the condition be?
Values less than 1.
Yeah, it has to be a convergent matrix. The eigenvalues all have to have absolute value less than 1. And possibly you can get some transient growth in there, which is interesting, and that can happen in some examples, but that's the goal. And so if someone gives you an A, and there may be classes of A for which you can prove, as David Young did back in the 1950s, certain convergence criteria for even more sophisticated versions of this, then you have a method that's very simple and ready to go. And so this is a standby of undergraduate numerical analysis classes.
How easy is it to find the splitting?
Well, if it's something like A is M is diagonal, or M is lower triangular, or some kind of weighted version of the lower triangle and diagonal and so forth, then all that works. And maybe if you have some class of A, you can prove that the spectral radius of n m inverse is always less than 1. Some of these methods, the successive over relaxation method, for example, has a parameter in it that you can tune and try to optimize the largest magnitude eigenvalue of the iteration matrix and so forth. Yeah.
Although these are indeed a mainstay of undergraduate numerical analysis classes, are these used in practice?
In my notes, I say they're basically, aside from like in contexts like multi-grid where they're used as smoothers, they're basically obsolete.
That was my impression.
Yeah. Because I think of this issue that you all are grappling with, which is how do you find a good M and a good N, right? Okay. So, Chris, do you want me to introduce cat smarts, or do you want to?
I'm going to do it very briefly, so you can spend as much time.
I will also do it briefly.
Maybe no one will. Let's do it.
I think I will let you all talk about cat smarts then.
Okay.
I have some notes for this lecture, just a brief summary that we can post or make available afterwards. It talks about cat smarts, which is basically saying that we're going to look for corrections to our iterate in the direction of particular rows of the matrix and doing that in an optimal way. Instead,
Just spell that so we can.
Oh, it's one
Thank you.
person.
Well, I always-
2 days.
yes. Do I pass the spelling bee? I'm terrible at spelling. That's right. Okay, good, good. Okay, well now I feel like I should tell you the method. Okay, 15 minutes or 20 minutes, I can't go into detail on that. Cat smarts, I understand, was lost in Poland during the Second World War. Another person with an interesting war history is Louis Fry Richardson, who was a conscientious objector during the First World War, wrote a book on weather modeling during the war that was lost at the front and then later recovered and was the foundation of the partial differential equations for weather modeling. Ended up in obscure academic positions because of his conscientious objector status, and ended up developing mathematical models for the arms race and all sorts of other interesting things. I think he should be better known. This is one of his, it's a method attributed to him. So the idea is that we have some xk and we're going to update it in the direction, call it gamma k, of the residual vector. So I'm just suggesting this might be a good idea. And it's maybe not clear why. That would be immediately, but we'll see why in a second here. Okay, if we just do a simple step and look at what the k plus first residual would be. Okay, so plug in the method, and we get, this is easier than the one on the left, minus axk minus gamma k rk. And here I end up with rk. Need an a somewhere.
What's the gamma k?
Just some constant, some real number, parameter that we'll tune in a moment.
Okay, that's the big one.
Yeah. Okay, so b minus axk minus gamma k a rk. And so I can have an rk here, and then I have a minus gamma k a rk, and so I end up with a formula I minus gamma k a times rk. And so now this is an analog of this formula right here, except maybe just a little bit more ambiguous because the kth residual will now be a product for j equals 1 to k of these terms, I minus gamma k times a times r0. There's a times there. But I want to emphasize this quantity here. What would that object look like? Yeah. Thank you. Good. Watch me like a hawk. Okay. So this quantity here, what object is this? So we multiply a bunch of these terms together. It's a polynomial in A.
So if you had the same gamma,
Then we'd have powers, right? And then you would just need the spectral radius of I minus gamma times A to be less than 1. Exactly, yeah. But there's the possibility we could tweak things as we go. So here I have some polynomial P of Z, which is the product of 1 minus gamma j z. And it satisfies a normalization condition, of course. If I plug in 0 here, then I get product of 1 minus 0, so I just get a bunch of 1s. So I like Richardson's method because it introduces this idea of developing polynomials in A and using them as a way of making an initial residual reduce in size. And so the question then becomes, how do we find good polynomials in A to make this quantity small? And in other words, we'd like not to have to guess a gamma k, but to have a way of automatically constructing that. And that's where we get to the GMRes algorithm and Krylov subspaces. So the kth Krylov subspace generated by the matrix A and the vector B is the span of B and AB and A squared B up to A to the k minus 1 B, which is to say it's the set of all polynomials Q in A applied to B where the degree of the polynomial is less than k. And this polynomial characterization of the Krylov subspace is really important to how we proceed. So the GMRes method, the generalized minimum residual method of Sod and Schultz, proceeds in the following way. It seeks to find x hat in this Krylov space to minimize the residual b minus a x hat. Okay. I won't talk about the mechanics of the GMRes algorithm because the tools you need for that emerge from the Arnoldi process that we use to compute eigenvalues of large-scale matrices that I'll talk about tomorrow. So tomorrow there'll be a little aside where I'll mention how GMRes mechanically operates. Here I want to talk about the theoretical level of what this algorithm achieves, not its implementation. So GMRes will find, I think I need a fresh board for this. The norm of RK written this way. Now, if we can think about this polynomial characterization, this is b minus a times a q of a times x hat. And if I, b. Now I can factor out that b. And you'll notice we have that same kind of expression that we had here for Richardson's method, that this is a polynomial, I minus a q of a. If I plug in 0 for a, I get the identity, 1. And I have a degree, generally speaking, k polynomial because of this extra a multiplying my degree less than k polynomial, q. And so now we get the classic GMRes optimization problem. I'll just say deg of p. And lots of people have spent lots of time thinking about this expression. Families have been fed on this expression. Okay.
How much gain is, let's say tomorrow somebody comes up with a new way to do this efficiently. Families are being fed.
By the convergence theory. Yeah, by the effort. So there's an automatic way to find this that's not cheap, but is optimal. And the question is, how good is it given properties of the matrix A? I just want to give you a taste of that convergence theory in 5 minutes.
Why is the degree of Q strictly less than K and now the degree of Q is less than or equal?
Because we have A times Q. So that promotes the degree by 1. Yeah. Yeah, good? Okay, and it's less than K because we have K vectors and the Krylov basis. Yep, you got it. Yeah, yeah. Okay, first of all, now we have the norm of RK is less than or equal to. If I do the natural thing and pull the B out, and it turns out Kim Chuan-To came up with an incredible example that there are matrices A for which when you make this inequality that seems so innocuous, you basically lose everything. That is to say, there is no B that makes this sharp. In fact, you can come up with an extremely arbitrarily bad example of that. But despite that, we don't know what to do otherwise. And so we still are happy making this step. Okay, so just two special cases. If we have a diagonalizable matrix, We plug in the diagonalization here. We have the norm of P of A less than or equal to the norm of V. We can factor out these eigenvector matrices like that. We can do an inequality between matrix norms. Again, we're using the induced matrix 2 norm. We have the norm of a diagonal matrix, again, using the 2 norm. The norm of a diagonal matrix is the maximum modulus of its diagonal entry. And so this is the condition number of V. Same condition number we saw at the beginning of the lecture. And then we're going to maximize over all of the eigenvalues of A. So now we're trying to construct a polynomial. We have some eigenvalues, lambda 1, lambda 2. I've drawn these real. We have 1 there. And we're trying to find a polynomial that goes through 1 and then hopefully is small over the eigenvalues. In my picture, yes. Yes, and only in the picture. When they're real, you can, and on one side of the origin, you can bound them with an interval. You can use Chebyshev approximation theory to optimize this. But what if this condition number is very large? So there exist perfectly nice matrices that are have very poor condition numbers. You're going to of the eigenvector matrix. Nikhil will tell you about them tomorrow morning. And in that case, this constant can be very large. And so as a convergence bound, this can be quite loose. And so for that reason, we seek other sets to look at. I'm going to just mention one here as I come toward the end of my time. We have a set W of A, which is called the numerical range of A. It will consist of X conjugate transpose, so maybe if I don't want to introduce new notation, conjugate transpose, where the norm of X in the, maybe I should say, to be, or maybe it's even better to say, called the numerical range. And it's a closed convex set that contains the spectrum. Okay. So if I shouldn't have erased my spectrum, I could have real eigenvalues like I did in that plot, and then the numerical range could be a much larger set that contains them in the complex plane. We then have the Crouzet-Palencia theorem from 2017 that says that for any function that's analytic on the numerical range, I'll just state it for polynomials, like the one we care about. The norm of the polynomial in A is bounded by 1 plus the square root of 2 times the max over the size of the polynomial on the numerical range. And Crouzet's conjecture is that this constant, which had been 11.08, could be, and was whittled down to 1 plus root 2, really is 2. So those of you that like hunting big game, that's a fun, open problem. Ann Greenbaum's done some lovely work on this problem and showed how you can replace the numerical range by other sets that kind of can carve out the origin, because if the numerical range contains the origin, and we need polynomials that are size 1 at the origin, they can't be smaller than that on the numerical range. So, okay, so this gives us another way of bounding the norm of P of A, and getting bound then on the GMRes algorithm here. Okay.
Is the idea that you don't have the eigenvalues of A, and so you use this as a the substitute?
Yeah, you don't, well, even if you knew the eigenvalues of A, this approach could just be too large. If this is of size 1, order 1, it has to be larger than or equal to 1. But if it was 10, this is great.
If the
Great.
matrix is symmetric, then it's no problem.
The matrix is symmetric, then it's size 1. And then you're golden. And that's, so it's 10:15 now. I want to have time for questions, but I also know we started a little late.
We have 5 more minutes.
5 more minutes, okay, to tell you about
Late.
everything. Okay. Quick question, yeah?
Yeah, so why is it faster to find x hat from the Krylov subspace instead of just the whole space?
Because the whole space, n-dimensional space, n is very large, I don't know where to start.
Okay, and
Right.
k is just small.
K is small, so yeah, I didn't give that context, but we're hoping, as if you can think of that plot I showed you earlier, Hen is giving you an algorithm that will allow you to converge in K equals 10 steps, or maybe even K equals 3 steps, or something like that, right? You promise?
Promise.
Okay, good, all right, excellent. So yeah, the idea is that K is much less than N, but that leads to I think a great point. I'll try to summarize a lot of material in just 5 minutes. This algorithm is expensive, and as you'll see tomorrow, it requires that you store a basis for what used to be here, the Krylov subspace. And as K gets larger, you're storing more and more and more vectors. Gene Golub had a bet that there would be a fast algorithm that didn't require you to store all of those vectors that applied to any A. We know such a method exists for symmetric A. It's called min-res, for example, or the conjugate gradient algorithm, or algorithms that are optimal for symmetric or symmetric positive definite A. Golub bet or wagered that would it be possible to come up with an algorithm like that for non-symmetric A, or show that none exists. And in 1984, Faber and Manteuffel proved that essentially no such algorithm can exist to, say, reduce the norm of the residual. And so they settled the bet, and that gave a license not only for GMRes, but also for a whole zoo of algorithms that now say, GMRes says, let's approach this problem by saying we have license to use long recurrences. And it's okay to do that even though that seems expensive by comparison to symmetric methods. The other approach is to say, let's stick with short recurrence methods that are faster per iteration, but are not optimal anymore. So either you compromise on the work or you compromise on the optimality. GMRes compromises on the optimality, on the work. You have a lot of work, but it gives you a nice convergence theory. The other methods compromise on optimality, and that becomes much harder to characterize. And it gives us a lot of different methods. The biconjugate gradient method, the biconjugate gradient methods stabilized, conjugate gradient squared, transpose-free QMR method, the QMR method, the IDR method. I'm sure I'm forgetting BiCG stab L. Okay, there are lots of methods that have been proposed, and it's not clear for general purpose problems which of these is best. Restarted GMRes. You just run GMRes for some steps, and then you just forget that you've done all that work. You throw your basis away and start over again with your new initial guess. All of those are possibilities that might work well within certain application areas, but are not, there's no clear winner overall. Yeah.
So I understand that symmetric matrices are overall just much better and easier. What if, but we're not exact, right? What if we have an almost symmetric matrix?
Yeah, then there are lots of interesting things that you could potentially do. And that sets up maybe this last thing I'll say, which is maybe you're solving the wrong problem.
One quick question.
Okay. Yeah.
Why is this WA easy to compute, or do I misunderstand?
I'm not so concerned about computation of, say, the spectrum or the numerical range, although it is actually not bad to compute. It requires you to compute extreme eigenvalues of symmetric matrices. But it's more of just a theoretical characterization. So we know if the numerical range is very large, or if the numerical range is favorable, then we can be sure that we're going to get good GMRes convergence, even if our problem maybe isn't even diagonalizable. So it gives a sufficient condition for convergence. Yeah.
So I don't quite understand how this is an iterative algorithm. If we
you're going to iterate on K.
Yeah, and then if I found like a polynomial for K, how do I produce one for K plus 1?
The algorithm that I'll detail tomorrow in the large-scale eigenvalue talk will give a very natural way of taking a Krylov basis that's k-steps and extending it by one more vector. And then that gives us a way of computing this optimal iterate, x hat, by solving a k plus 1 by k least squares problem.
Okay.
But the details will have to follow tomorrow.
And I will talk about how to optimize it on Thursday.
Okay, good. So I better set the stage for that. The last word is that maybe ax equals b is the wrong problem to solve. And I've alluded to Hen's work here. Maybe what you want to do is take some matrix M inverse. So implicitly, I'm suggesting that M is invertible and easy to invert. And solve instead that problem. Or maybe AM inverse y equals b. Or maybe ML inverse A, MR inverse Y equals ML inverse B. So these are three different flavors of what we call preconditioning. And from a practical standpoint, this is essential, particularly for problems where we might know a lot about the structure of the underlying A. It's a discretization of an operator, and we have a lot of spectral asymptotics for that operator, and we know, quite a lot about its properties, maybe even approximate eigenvalues and eigenvectors, and maybe then we can construct a matrix that does a lot of the hard work. So I have an A that's symmetric plus small in some sense. Maybe then I can choose my M to be the symmetric part. And so you have A equals S plus E, and then you're going to use S inverse as your preconditioner. And then you're going to have an identity matrix plus S times E. Maybe E is low rank, in which case this is going to converge in whatever the rank of the matrix is, or maybe plus 1 steps. Maybe E is just small in norm, and then the numerical range of this set will be bounded by a disk of radius norm of S inverse times E. And so I can guarantee fast convergence by this convergence bound. So it's a lovely setting in which to think about preconditioning. Changing the problem to give it spectral properties, either a nicer eigenvector condition number and better eigenvalue distribution especially, or a nicer numerical range that allows you to get faster convergence. Good place to stop?
Wonderful.
Okay, thanks. Okay, happy to take any. Thank you for all the good questions. Yeah.
Maybe there are more questions or comments.
Do any of these methods have worst case guarantees over a large class of matrices?
I kind of think of these as worst case guarantees. That work for quite large classes of matrices. I didn't mention one of my favorite subjects, pseudospectra, which is another way of bounding nor P of A, but I restrained myself. But yeah.
This requires some knowledge of the spectrum, some delicate knowledge of the spectrum. Is there a more kind of flat box kind of results?
Often for classes of problems. So you might have saddle point problems. There was an example in the exercises where A is a 2x2 block matrix that has a 0, 2, 2 block. And that structure comes up in all sorts of applications. And there's a beautiful preconditioner that Murphy, Golub, and Wathen designed that when you apply that preconditioner, you're guaranteed fast convergence of GM-res in a way that that problem makes specific. Yeah.
Discrete elliptic PDE.
Right. Right, so like in a very important class of application problems, maybe with variable coefficients where you can precondition with the, with a constant coefficient case that you can write down a solution to, or there's all sorts of things you can do. Use multi-grid preconditioners, yeah.
But how do you estimate this maximum PZ on the numerical range?
Oh, that gets into potential theory. And so we now have a set in the complex plane. We're trying to solve an approximation problem over this closed convex set of the complex plane. And you can bound that set with a polygon, say, and you can use Schwarz-Christoffel mapping. It's often quite circular, so maybe you just want to bound it with a disk or an ellipse that you know potential theory for, and that will give you an asymptotic convergence rate.
Okay.
Yeah.
Is there I guess, a condition on A that would say that the numerical range is not too much large? I guess not not too large.
Yes, the condition is that the eigenvalues of the Hermitian part, A plus A transpose over 2, can't contain the spectrum within its spectral interval. So all the eigenvalues of A plus A transpose over 2 have to be to the right or to the left of the spectrum.
Of the origin. Oh, the spectrum over the origin.
Sorry, the origin. Yeah, thanks. Yeah, they got to contain the origin of the spectrum. Yeah, thanks.
Yeah, I understand the numerical range contains the spectrum, but is it like maybe a more geometrical interpretation of what it actually is or describes?
Yeah, so these quantities here we call Rayleigh quotients, and there's the natural way of taking a vector x and turning it into an estimate of the eigenvalue. You can imagine if x was an eigenvector, a times x would be lambda x, and then the rest would cancel and you'd be left with lambda. So that's how you prove that the spectrum is included in this set. But it then also includes every kind of reasonable estimate of an eigenvalue.
Maybe one thing to add to this is this: whenever A is normal, you've got a really nice, beautiful convex hull.
Yeah, thank you for mentioning that. Yeah, if A is a normal matrix, meaning it commutes with its adjoint, then A transpose A equals AA transpose. Then, as Olga mentions, the numerical range is the convex hull of the spectrum. And you can write this and see this as a convex combination of the eigenvalues in the complex plane. So that's a nice case. In that case, again, this is 1, and you might as well have just used this bound.
Last question, I'd say.
Would you ever want to pass to the symmetric case by solving the normal equations?
Oh gosh, I have that in my notes and I forgot to mention that. One of the problems deals with a case where the normal equations are quite nice and GMRes is quite nasty. So just for the uninitiated, the normal equations is to, in a sense, precondition with A transpose. And this looks bad in the sense that it kind of squares the eigenvalues here and spreads them out in a way that can make them small ones closer to the origin and large ones farther to the origin and make this a harder approximation problem. But for some problems, it's actually quite nice. So if I have a method for solving symmetric systems, then this can be very efficient. It's positive definite. It requires a matrix vector product with A and with A transpose at every iteration, and you may not have A stored in a way that makes that favorable on your computer. But if you're willing to do this, then that's a kind of an easy approach. Yeah, I should have maybe mentioned that. Yeah, thank you for...
Okay, I think let's take a 15 minutes break.
Good, sorry.
Thanks again.
That'd be fun.